Welcome student. I am Shadev Hake, ANTC Department, PICT Pune. Today we are going to demonstrate the new practical of RMT subject. Our title is to measure and verify port characteristics of microwave teas like E-plane teas, H-plane tea and EH-plane tea, or is also known as magic. Our objective is to verify the performance of E-plane tea, H-plane tea and magic tea with its theoretical and practical reading. So today we will perform the first tea, that is a E-plane tea. For E-plane tea, we will use this block diagram. In this block diagram, our first block is nothing but a klystron power supply. This power supply will give two type of voltage. One is a beam voltage and another is a repeller voltage. Second block is a klystron tube, or it is also known as reflex klystron tube. This klystron tube generates a microwave signal. That's why this tube acts as an oscillator. The operating frequency of this tube is nothing but X band. That means from 8 GHz to the 12 GHz. Our next block is an isolator. In previous experiment, we saw the operation of isolator. Here, isolator is a one-way communication device. It transmits information from port 1 to port 2 and it blocks the information from port 2 to port 1. That means it isolates the reflected signal from output side towards the oscillator and it keeps the stability of our oscillator. Stability means operating frequency of oscillator. Our next block of this block diagram is nothing but cavity resonator. We know that microwave frequency we cannot measure by using the CRO or DSO. To measure the microwave frequency, we are using a cavity resonator, or it is also known as a frequency meter. And we saw in a oscillator characteristics how to measure the operating frequency of any microwave signal. Our main today's experiment component is nothing but a DUT, device under test, and those DUT are nothing but E-plane tea, H-plane tea and EH-plane tea. This EH-plane tea is also known as a magic tea. Why it is known as a magic tea, we will see later. Output of one tea will send towards a detector. Here detector is used to detect the electromagnetic signal. There are many types of detector in a microwave, like a pin diode detector or Schottky barrier diode detector or different type of detector. Out of those, in our lab we have a Schottky barrier diode detector. Output of detector will send towards a CRO or DSO. By using the CRO or DSO, we will measure the actual voltage of our electromagnetic signal. So today we will perform the E-plane tea, H-plane tea and magic tea simultaneously. So our first component is a E-plane tea. Our first device under test is nothing but a E-plane tea. So in this E-plane tea, we will see the actual structure of E-plane tea, working of E-plane tea, and then we will see the performance port characteristics on our actual experiment. So this is a structure of E-plane tea. Here, this is your actual waveguide, and we are connecting a one another side arm to a actual waveguide. This is your side arm. So this portion is known as a junction. Here this plane T is known as a E plane T because electric field of this primary waveguide is looks like this. My pen cap is nothing but a direction of electric field. Yeah. And here axis of my side arm is nothing but a blue pen. Axis of side arm is nothing but a blue pen, and red pen is nothing but a electric field direction. So here axis of the side arm is parallel to the electric field. That's why this plane T is known as a E plane T. E plane T. This is in E plane T. This portion is my port 1. This is my port 2, and third is nothing but my third port. This port is also known as a ER. Yes. So if we place my E plane T here in this block, so structure looks like this. Port 1. So here this is my port 1. This is my second port, and this is my third port. So got the point? The meaning of E plane T, why this plane T is known as a E plane T. If we see the structure of E plane T, in which this is a port 1, this is a port 2, and that is your port 3. If we see the front view of E plane T, it looks like this. This is my front view of E plane T, in which this is my port number 1, this is my port number 2, and this is my port number 3. So here this is my primary waveguide, that is known as a collinear waveguide, and this is my side arm is known as a ER. Here direction of electric field is nothing but this direction, and we know the direction of axis of side arm is also this. Both are parallel to each other. That's why this plane T is known as a E plane T. Now let us see the working of E plane T. Suppose consider your E plane T is connected in between your block diagram. Yeah. Apply some input from the source towards a E plane T. So here this is my input port number 1. Here this input port will transmit the information to the port number 2. Yes. So connect a detector to the port number 2 as an output, and in a port number 3 we will connect a match terminator. Match terminator. So in this way we can determine the input and output across a E plane. In second case, what we will do? We will use my port number 2 as a input, port number 1 as a output, and my third port will be a cell, that is a match termination. So in this case you will get a output like a previous output, because our case are same. We are changing only input and output position. We are keeping the third port constant. Yeah. Now let us change the scenario. Our scenario is apply the input to port number 3. Apply the input to the port number 3 and measure the output across the port number 1 and port number 2 also. So in this case, what will happen? We will get a magnitude across the port number 1 and 2 same but out of phase. That is 180 degree. This is a specialty of E-plane T. In E-plane T, if we connect the input to the port number 3, we will get a magnitude across the port number 1 and port number 2 same but out of phase. Out of phase means 180 degree. Yeah. Now if we do the different thing means case number 4. Let's assume apply the input to the port number 1 and port number 2. Here we will apply a same magnitude input of same phase. Okay. And if we collect the output across the port number 3, so here what we will get? We will get a 0 output. So output of the third port is equals to 0. That's why this E-plane T is act as a subtractor also. If you see the structure of E-plane T, look here, this ER or side R is in the series of main waveguide. That's why this E-plane T is also known as a series T. Now see the main waveguide and side arm junction. It looks like a voltage junction. Yeah, the voltage across this R and voltage across this R is nothing but your voltage. Yeah, so this E-plane T is also known as a voltage junction. Yes. So practically we will perform the E-plane T and we will match the parameters of E-plane T with a theoretical parameters by using the S matrix. Thank you. We saw the E-plane T. Now let us see the H-plane T. So our today's practical is nothing but a H-plane T. The block diagram and or a experiment setup for a E-plane T is nothing but your H-plane T. Only difference is that here our device under test is nothing but a H-plane T. So already we have seen the operation of every block in a E-plane T, same operation in a H-plane T also. So let us see the structure of H-plane T and then we will see the operation of H-plane T. So look here, this is a H-plane T. Look the 3D geometry. Yeah. So in which this is your primary waveguide or is also known as a collinear waveguide, and this is your side arm or is also known as a H arm. So we can see the 3D geometry front view of your H-plane T looks like this. So in which this part, port number 1 and port number 2 is your primary waveguide or is known as a collinear waveguide, and your this part is nothing but a side arm or is also known as a H arm. So here we will write or we will refer this port as a third port. So let us see the operation of H-plane T and then we will see why it is known as a H-plane. Look here, if we apply the input to the port number 1 and if we apply the output to the port number 2, so your third port means a HR, here we will apply the match termination. Yeah. When we apply the port number 1 through this source. Here the direction of electric field is nothing but this direction. And we know, according to the electromagnetic theory, when your electric field direction is looks like this, so magnetic field is nothing but this direction. So my blue pen is nothing but a direction of magnetic field, and my red pen is nothing but a direction of magnetic field. So look here, the axis of the side R is parallel to the magnetic field. Once again I repeat, my scale is a axis of the side R, and this side R is parallel to my magnetic field. That's why this plane T is known as a H plane T. That's why this plane T is known as a H plane T. Now let us see the working. My port 1 is a input. My third port is a match port, means there is a perfect matching. So definitely I will get a output across a port number 2, and that output we can measure by using a detector on a CRO. This is a case number 1. Case number 2 is nothing but apply the input to the port number 2, measure the output across the port number 1. That time your third port is a match port. So here definitely we'll get a output across a port number 1 also. My third case is apply the input to the port number 3. Measure the output to the port number 1 and port number 2. So here don't connect a match, use a CRO or DSO through the detector. So what will happen here, when we measure the output across the port number 1 and 2, here we get a half output, in a same phase. This is a difference between a E plane T and H plane T. In E plane T, if we use a third port as an input, and if we measure the output across a port 1 and port 2, we get a same magnitude but out of phase. In H plane T, we get a half magnitude, means same magnitude across a port number 1 and port number 2, but in same place. Yeah. Now last case is nothing but case number 4. Already we have discussed. Case number 4 is apply the input to the port number 1. Apply the second input to the port number 2. Here let us assume we are using a second oscillator on a right hand side. Yeah. So here apply the input to the port number 2. Measure the output across the port number 3. So here we will get a addition of 2 sources across the port number 3. Addition of 2 sources. That's why this H plane T act as a adder. Got my point? Any doubt? Yeah. Now look a structure of H plane T. 3D geometry. Okay. Now see here the difference between the E plane T and H plane T. In E plane T, my side R is in the series of main waveguide. Here in a H plane T, my side R is in the shunt to my main waveguide. That's why this plane T is also known as a shunt T. Shunt T. In a E-plane T, we know here we are measuring a voltage. Yeah, that's why it is known as a voltage junction, because voltage is related to the electric field. But in a magnetic field, here we are measuring a magnetic field. And according to the electromagnetic theory, magnetic field is related to the current. That's why this plane T is also known as a current junction. Current junction. So this is nothing but a theory of E-plane T, H-plane T. Already we have seen the E-plane T theory. This is a H-plane T theory. In a actual practical, we will demonstrate the practical and we will see the actual reading with a theoretical reading by using the S matrix. All of you know that what do you mean by S matrix and how to solve S matrix in E-plane T and H-plane T. We saw E-plane T and H-plane T. Let us see the EH-plane T. Name self indicate that combination of E-plane T and H-plane T is nothing but a new T and is known as a EH-plane. Look here in this 3D geometry, this portion is your main waveguide, this portion is your ER and this portion is your HR. Yeah. So if I place this my EH-plane T in your device under test, we will get the working and we will get parameters related to the port characteristics of EH-plane T. So this is our simple block diagram related to the port characteristics of EH-plane T. Yes. So already this block diagram we have referred in the E-plane T and H-plane T. Same block diagram we will use for a H-plane T. So in this block diagram, only difference is that my DUT, device under test, is nothing but a EH-plane T. Yeah. EH-plane T. So physical structure of your EH-plane T, it's look like this. Yeah. If you see the front view of this EH-plane T, and if you draw on your paper or board, it looks like this. This is my front view of EH-plane T. In which this is my port 1, this is my port 2, this is my port 3, and this is nothing but a port 4. Yeah. EH-plane T is also known as a magic T. Yeah. And the reason behind the magic T is nothing but your operation. So let us see the operation of EH-plane T and then I will tell you why it is known as a magic T. Yeah. So in our first operation, let us apply some source to your EH-plane T at the port number 1, means here. So here we will apply the port number 1. If you look at your EH-plane T internally, it looks hollow. And we saw the operation of your E-plane T or H-plane T. Here, when we apply some input to the port 1, always we get the output across the port number 2. But in a magic T, if we apply the input to the port number 1, we will not get a output across a port number 2. That's why this is known as a magic T. This is the one reason, first reason why the EH-plane T is known as a magic T. Yeah. Second magic, so here your case 1 is nothing but apply the input to the port number 1. Second magic is nothing but apply the input to the port number 2, measure the output across port number 1. That time, in previous time and this time also, your port number 3 and 4 are nothing but a match port. Yeah. So in this case also, if I measure the output across a port number 1, that time also we are not getting a output across the port number 1. Yes. This is a another second magic related to the your EH plenty. Look here, your E and H plenty, combination of E and H plenty is nothing but a totally hollow tube in between a port 1 and port 2. Then also it happens. Yeah. Third magic related to the your EH plenty is nothing but apply the input to the port number 3, match a port number 1 and port number 2 and measure the output across the port number 4. So what is your guess here? Will we get an output across the port number 4? Yeah? No, absolutely not. So output across the port number 4 is nothing but a 0 magnitude power, or it will be a very very low power in a nano or pico. Yes. So look here, structure of your E and HR. This is your ER, this is your HR. We are applying the input to the HR, means port number 3. Yes. And we are measuring the output across the port number 4. But here we are not getting a output. This is your third magic related to the EH plenty. Fourth magic related to the your EH plenty is nothing but apply the input to the port number 4 and measure the output across a port number 3. In this case, your port 1 and 2 both are the match terminated. So tell me, what will happen here? Will we get an output across a port number 3? Yes, absolutely. Your answer is a no. We are not getting the output across a port number 3, and that's why this is the fourth reason related to the magic. Yeah? And fifth reason related to the your this EH plenty is nothing but if we check a match termination across this junction. So here if we get a matching of any two terminal, remaining terminal automatically match. And this is a fifth reason EH plenty is known as a magic T, and hence we can write the study of EH plenty, or it is also known as a magic T. What my meaning? So this is a theory related to the your magic T or EH plenty. We will see some port characteristics related to the E plenty, H plenty and magic T, and we will see the experimental parameters, or we will match a experimental parameter with a theoretical parameter by using the S matrix. Yes, all of you know that how to solve the S matrix. We saw why the EH plenty is known as a magic T, but we haven't seen when we will get output, at what port. Yes. So look here, let us assume input to the port number 1. We know output across the port number 2 we will not get, but we will not keep open as a port number 2. will connect a match termination. Yeah. We will measure output across the port number 3 and definitely we will get some output across the port number 3. That time we will keep your port number 4 as a match terminal. This is a one case. Yeah. Then we will do the another case. We will apply the input to the port number 2, or we will keep a port number the same. That is the input at a port number 1. We will change the output port. We will keep a output port as a 4 and match termination as a 3. Yes. So in this case also definitely we will get the output across the port number 4, because according to the magic we will not get output across the port number 2. Yeah. This is a second case. Third case, apply the input to the port number 2, match a port number 1 and 3 suppose. Match a port number 1 and 3 and measure the output across the port number 4. So definitely we will get a output across the port number 4. How much output we will get? We will see in a practical, and that output we should match with a theoretical part, means a S metric calculation. Yeah. Now see the next case. Input is a 2, but output is a third port. That time your first and second port are matched port. So that time your first 1, 2, 3, 4, 1 and 4 port are a match port. So yes, according as per your previous theory, you will get output across the port number 3 also. Yes. Then take a next case. Next case means what? We saw the input across the port 1 and input across the port 2, but we haven't seen the input across the port number 3. What will happen? What will happen? So apply the input to the port number 3, match a port number 1. Sorry, let's take a match a port number 2 and 4. So remaining port is nothing but port number 1. Port number 1. So definitely, if I apply the input to the port number 3, if I do the matching of port 2 and 4, so we'll get output across the port number 1. Yeah. And do the reverse case also. Reverse means what? Apply the input to the port 3 as it is. Keep your 4 port and first port at a match position and measure the output across the port number 2. Definitely you will get a. Yeah. Do the same thing for a different cases. Yes, means apply the input to the port number 4 and measure the output across the 1 and 2. That time keep your 3 and remaining port matched at a position. Yes. So definitely you will get the output as per your magic tree theory. Yes. And what we will do? We will see the practical port parameters and we will match those practical port parameters with a theoretical calculation like a S matrix calculation. Thank you.